The world moves fast, no doubt about it. Commerce moves with it, making our choices more numerous than we could have imagined just a couple of decades ago. Change happens. For decades, America needed to protect itself from obvious aggressors. At the same time, space was a frontier, begging for exploration, and America began to reach out with wonder into that expanse. So the country turned to companies like Chemical Systems Division, CSD. So how did CSD evolve? How did we become one of the leading manufacturers of propulsion systems? At the end of World War II, mistrust between the United States and the Soviet Union turned relations between the former allies frosty. As adversaries, each country worked to keep an eye on the other. Space provided a window to do that. When the Soviet Union launched Sputnik, national pride and security demanded that the United States counter.
After Sputnik, there was an enormous outcry in the United States. We can't let the Russians beat us.
The space race was on, with the United States left at the starting gate. There was a national urgency to make up lost ground. And in that urgency came a need for a large solid propellant booster that could be easily shipped coast to coast. Barney Adelman conceived of building a segmented booster and approached Herb Lawrence about the idea. Herb devised a way to assemble the segments. The two realized the potential and enticed Dave Altman to join them, forming a new company, United Research Corporation of Menlo Park.
We had raised enough money to get the company started, but we didn't have enough money to do the things we wanted to do. So we had talked to Boeing and to Ford, among others, and to United Aircraft Corporation. When we talked to United Aircraft, their idea was that, well, before we can start making big rockets, we've got to develop propellants and so on, and we'd like to call it United Research Corporation.
Ford and Boeing offered more money to participate in the fledgling company, but the three visionaries felt that United Aircraft would be a better parent.
They put up $17 million for their part of it. And we started looking around for a place to set up the plant and so on.
None of the three men were yet 40 years old. While their concept was strong enough to be patented and to create a partnership with a major company, they believed they needed additional credibility to enhance prospects of substantial contracts. So they turned to Lieutenant General Donald Putt, who was retiring from his position as head of the Air Research Defense Command. General Putt brought more than the credibility the three young men believed they needed. He brought a career's worth of contacts within the Air Force. With the leadership team and funding in place, the company focused on the developing segmented solid fuel rockets. The brightest engineers were sought to help.
When I joined, there was an article in Business Week that referred to the top 40 people in the rocket industry. At that time, 20 of them worked for United Technologies Center.
The engineers were covering new ground, calculating possibilities with rudimentary tools like slide rules, often empirically learning what worked and what didn't.
The early years of propulsion required a substantial amount of tests to verify theories. That's because in those days we didn't have the sophisticated modeling techniques or the computers available to run those models. And a lot of that was done with intuition. A lot of it was done with minor tests in labs, but very little was done by analysis.
We had a big Burroughs calculator, serial number 1, but it was used mainly for business purposes and very little engineering. Work was done by young, energetic, enthusiastic kids that didn't know how to fail.
In fact, success came early to CSD.
We were fortunate to get a NASA contract to build segmented motors. And these were conical motors at the time. They were built as cones, starting narrow at the top and widening as you go down. Why did we have that concept? As you see internally, the hot combustion gases travel down the port. And as they travel down, more and more gas is being added to it as you move down. So you had to expand the opening in order to accommodate the gases. So that was the conical concept. And the contracts that we had with NASA at the time were proving out that concept, and they were known as the P1 and the P2 motors.
Then the Air Force offered a contract to design, build, and test the concept of a segmented rocket. Though CSD bid on the job, the company didn't yet have the facilities or the staff to meet the contract's requirements. But the stars were lining up for CSD.
At the time that that RFP was issued, I think we had about 12 people, and we had a few more lined up but hadn't joined us yet. But in any event, we bid it, and the competition went on for 3 or 4 months, during which time we were acquiring people and building the facility at Coyote. Well, there came time for a decision, and one of our competitors thought they had lost, and they filed a formal protest that the competition was not conducted fairly. The Air Force looked at that for a while and then canceled the competition. Now, as it happened, the group that filed the protest had won, but they didn't know it. And so it was held about 6 months later, perhaps a little longer than that. This time we won.
Winning the Air Force contract to build a segmented solid fuel rocket led to CSD winning the contract for the Titan program. For a company so young, the challenges were just beginning.
When we won the Titan program, we had a daunting task. We had a task to put together everything literally from the ground up. We had to build a complete facility and plant. We had to hire several thousand people. We had to put together a vendor-supplier team of hundreds of suppliers and vendors. We had to assemble all of this and produce the largest solid rocket propulsion system at that time in the United States. And it was a wonderful experience. And I think what was exhilarating about the program was we didn't know whether the Titan was going to work. We wanted so much to make this motor a success, not only for ourselves and for the company and for the Air Force, but for the country, because at that time we were in the post-Sputnik period, and our national pride was sort of on the line. We all seemed to have a can-do attitude, an attitude that said, we don't fear failure, but we're determined we won't fail.
That determined attitude was tested on several occasions. Engineers faced some significant challenges while they were designing Titan, particularly because of the rocket's size. Nozzles were just one of the challenges.
They'd been made of carbon before. The flame temperatures are in the range of 5,000, 6,000 degrees Fahrenheit. And if you subject any material to that sort of temperature for more than a minute, it starts to burn up. Things or melt or otherwise be destroyed. We developed a type of carbon that was very hard and could be molded into very large pieces for the throats. Now, these were not little nozzles. You have to remember that until we came along, rockets of over about 150,000 pounds thrust were unusual.
Oh, there's one other thing, the ignition system. How do you ignite a big motor like this? You know, on the very little motors, you have, a spark plug, maybe a little methane and oxygen, that sort of thing, or a match, what have you. But here's this big monster now, 10 feet in diameter with a big opening, and the port opening was over 3 feet in diameter. How do you ignite that? I said, well, let's ignite it with a small rocket motor.
A third challenge was brought by the size of the motor's case, which was 120 inches in diameter. The weld that had to hold the case together needed to be completely void of defects, or the motor could be lost, making for some anxious moments during static testing.
I happened to be standing next to Doug North when we had one of those first static firings. After it was over, I looked at Doug, he looked at me, and the first thing we said to each other was, wow, 2 minutes is a long time, and it seemed like an infinity.
CSD engineers overcame the design challenges, but not without some setbacks. After all, sometimes prototypes fail.
We had one failure in the program at Edwards in which the insulation was not properly attached to the body, and it burned through. Interesting little sidelight on that, incidentally. That was covered by many, many reporters, and one was a lady from the Chicago Tribune. We were about 3 miles from the actual launch site. We had a very good view of it with binoculars and so on. And at about 30 seconds, we could see something was going wrong. The case was getting red hot at one point, some point in it. This lady looked at it and said, gee, that's beautiful. And then it exploded, and she said, this is magnificent. Do you do that every time? And we said, no, we try not to.
Ultimately, in June 1965, only 3 years after receiving the Air Force contract, it was time for Titan's maiden flight.
And there was this big monster sitting on the pad, and we're all watching breathlessly. And that was the first time that I was that close to a very large system. I'd watched flights before. I'd watched a V-2 flight, and that we flew, and some of the others of the Army flights, but this was the first large one. And there was the countdown, and then the big roar. And as it went up, you could feel your diaphragm vibrating with the jet exhaust. You have to be there to feel it. And it took off, and we were watching the thing, and watching it as it turned over into the horizon. And it was just a great feeling.
When you fly one of these things, there's a tremendous feeling of satisfaction and gratitude to all the effort that went into the development. The fact that this vehicle went together in 3 years and flew successfully was utterly remarkable. Those of us that watched it fly for the first time almost didn't believe it, because it was a tough job.
And I believe we were motivated by a sense of purpose, a sense of mission. We knew we were working on something. We sensed that it was bigger than each of us individually. That may sound corny, but that's the way we felt. We felt that this thing was bigger than us. And, you know, there was a national pride at stake. And I think that we felt that what we were doing was important to our country.
CSD's innovative work on segmented solid fuel rocket boosters paved the way for Titan and put the company on the map. Without the breakthrough, other launch vehicles like the Space Shuttle may not have been possible.
We, in fact, inaugurated a new concept of launch vehicles, which would not have been possible without the invention of the segmented solid rocket. You couldn't have done it with monolithic rockets.
CSD's innovations paved the way for other launch technology. The large solid fuel boosters used on Titan needed small separation motors to peel them off of the core vehicle. The Space Shuttle needed similar boosters and similar separation motors.
We had a very demanding situation imposed upon us by NASA, that we could not eject anything out of our rocket motor that could possibly damage the orbiter. So we had to come up with a propellant system that was virtually aluminum free, and we settled on a formulation that has 2% aluminum. Now, we couldn't use any other materials in the rocket motor that could eject particles either. So we had to design a nozzle with graphite and actually steel, but designed the steel in an area where there was no melting of the steel.
Titan was a workhorse for CSD and the United States. But there were other innovations from CSD. One was IUS, the inertial upper stage.
At about 1970 or so, and the shuttle was under development at the time, the Air Force and Department of Defense needed a good upper stage that was very versatile and be able to put payloads not only in low Earth orbit, but into synchronous orbit. And all the big prime contractors were looking at it, and each one had their pet approach.
The prime contractors were focusing on a liquid system approach.
I began to think about it. I said, well, they're all married to their particular stages. They want that in the business, but we're not. So let's free up our thought process. And instead of using one of those stages, why not just use two solids? One specifically for the perigee and one specifically for the apogee.
Altman thought Boeing might be interested in working with CSD because Boeing didn't favor a method the way other prime contractors did. It took some convincing, but Boeing finally realized the value of the CSD concept and agreed to be a partner, to the benefit of both companies.
There were some key technologies that were very important. One was you had to build a very efficient stage to perform in space. And so you wanted a light case, you wanted a high mass fraction. Another key thing was that we wanted a pretty high performance, and that involved a development called the ENEC or EEC, Extendable Exit Cone. It was a means of building a very large nozzle to a very high area ratio. So the filament wound motors and the large nozzle, these were some of the key elements in the success of the IUS program.
What this led up to was our first flight, which was in 1982. We flew in October. We flew on the Titan 34D, and it was the maiden flight of the Titan 34D as well as the maiden flight of the IUS. And to make it even more spectacular, the launch took place at midnight so that we lit up the whole sky with the Titan lifting off. And it was just an absolutely spectacularly beautiful flight. We had a couple of discus satellites on board, a DoD type mission, and it worked super. Now, the IUS was qualified for both flight on the shuttle and the Titan. And so in April of 1983, we had our maiden flight on the space shuttle, STS-6. Now, we've had the really neat opportunity here to have put some really, really important payloads either into orbit or off to other planets.
The success of IUS involved CSD in some of the country's most important missions to space, delivering on the goal of mission success.
We've taken the TDRS satellites, which are the communication satellites that NASA uses for the space shuttle. We put Galileo out to Jupiter, Ulysses to the Sun. Magellan went to Venus and mapped the surface of Venus for a long period of time. And most recently, we put the X-ray telescope up called Chandra. And so we've had some really, really exciting missions that have a lot of visibility at times to the man on the street, so to speak.
Despite the success with large solid rocket motors used for space, it became clear that CSD needed to diversify its offerings. The entry into the tactical and strategic market proved important for the company.
The vision of Al Medica, who expanded our base business from one of a single program, Titan, into one of multi-programs, is what continues to bring success to CSD today. He was successful in the Minuteman program and bringing on the additional efforts associated with programs like Tomahawk, Mark 72, and the expansion into the THAAD program.
So it was a business decision for us to proceed into that venture. So we looked at the tactical business as a new market to enter. One of the drawbacks we had was we had no experience in tactical missiles. And so we actually went off and demonstrated our technologies in a full-scale demonstration. Now, of course, demonstrating that technology on something the size of a Titan would be cost prohibitive. But something in the size of the tactical market, that's how you enter the market, is to show them that you can build it and demonstrate it. And that's exactly what we did with the Tomahawk.
Tomahawk cruise missiles used by the U.S. Navy have a precision strike capability against key enemy targets. This program brought together a number of concepts that were successfully developed by CSD.
Well, this was an exacting mission for us because the Mark 106 had a limited volume, had to fit in the right launch canister of a certain size. So we packed 20% more performance in that package with a more improved propellant, and we changed the nozzle system.
After that first win in the tactical arena, CSD sought other contracts. America's fleet of land-based Minuteman ballistic missiles, designed and built in the 50s and re-engined in the 70s, were aging out and needed to be remanufactured.
And it was a good fit for our company because it was, the same kind of system for a different customer, the Air Force. And there was a cost competition performed, and CSD won that competition on the basis of price. First of all, we had significantly taken on a large challenge in terms of the price we could make the system for, and learning how to restart suppliers that hadn't made these products in 10 or 12 years because the Air Force had decided that they wanted and demanded us to use the suppliers that made all these parts and components in the past. A lot of them had not made those parts in many years. They'd lost the formula and had to learn again.
At about the same time CSD won the Air Force's Minuteman III Stage 3 remanufacture contract, it also developed the crucial Class 1.1 propellant system under the leadership of Dr. Ross Felix, Vice President, Research and Advanced Technology, and won the contract to build the third stage motor for the Navy's submarine-launched Trident II D5 Fleet Ballistic Missile.
The D5 program became known as the Golden Program at CSD, primarily because it made its way through its entire development phase, all of its static tests, all of its flight tests, and to date, all deliveries and reliability tests with complete success. We delivered some 400 of these. They were all made with very low defect rates and high technologies. We upgraded the technologies during the actual production phase, changing from a Kevlar motor case to a carbon motor case, graphite motor case, and carried on what I'll have to say was probably the best conducted program in the history of the division.
CSD enjoyed unprecedented mission success, and under the leadership of Dave Lee, CSD transitioned into a multifaceted production company. Success, however, sometimes leads to complacency, and complacency leads to unexpected setbacks.
We had flown Titan successfully for 23 years, and it got so routine that Titan flights were not even recognized or announced at CSD any longer. And I'll never forget standing outside of the engineering building and somebody come running out and said, "Doug, the Titan failed." That was April 18th, 1986, 10:30 a.m. in the morning, and it was a feeling in my stomach that I'll never forget because the Titan was there always, and for a failure to occur was something that all of us had never even thought about something like that could happen.
Failure never comes at a good time, But the Titan failure had a disastrous effect on the military surveillance of the world, so critical to the country's national defense.
The event occurred when we had just been through the shuttle failure, the 51L failure, and that meant that this nation had no capability whatsoever to launch heavy satellites. And all of a sudden, we went blind. And our satellites at that time were aging out.
The Titan fleet was aging, but there was no program in place to provide the necessary information on the effects of aging on the fleet. Over 2,000 people from United Technology Corporation and Martin Marietta worked around the clock for 15 months to determine not just the cause of the failure, but the flight status of the existing Titan fleet.
The Titan rocket failed because the insulation protecting the rocket motor case became weak, and the accelerations of the rocket with the weight of the propellant pulled the insulation away from the steel wall, allowing hot gas to get behind the insulation, burning a hole in the case, and the entire rocket failing. The overall Titan program benefited immensely from this evaluation in the sense that until a failure occurs, you don't really understand how the rocket worked. And it's an expensive way to learn, but from that reanalysis and reinspection, we learned more about the Titan rocket than had ever been understood before.
Contract success continued for CSD in the tactical market when the company landed the contract for the Mark 72 booster to extend the range and capability of the Navy's Aegis Fleet Air Defense System. While working on the project, CSD engineers brought yet another innovation to the industry. The Mark 72 incorporated the first high-voltage TVA system for vectoring the nozzles.
The Mark 72, with its 4 nozzles on the back of the rocket, contains the most sophisticated 4-nozzle technology of any rocket flying today.
CSD continued to actively compete for and win additional contracts. Lockheed was chosen as the prime contractor for THAAD, Theater High Altitude Area Defense, a ground-based weapon system developed specifically to defend against theater ballistic missiles. CSD overcame heavy competition to be chosen for THAAD's booster propulsion.
The length to diameter ratio of the THAAD booster is the highest anybody's ever made. We committed to demonstrate our capability by building and test firing the THAAD booster with the TVC. Of course, that's one of the measures that we've liked to tout ourselves with for many years. We did that from start to finish in 113 days, including making the chamber, the nozzle, the TVC, packaging the whole thing together, and test firing it at CSD successfully. And we think that was a key element that helped Lockheed win the program in that major competition.
In 1999, THAAD scored its first successful intercept, completed the demonstration validation phase of the program, and began the engineering manufacturing development phase. United Technologies Corporation recognized the importance of space for future growth and joined CSD with Pratt & Whitney Liquid Space Propulsion to form Space Propulsion Operations, positioning CSD to support the world's space industry. When the opportunity arose to compete for the Air Force's propulsion replacement program for Minuteman, CSD took a risk that paid off in winning the contract.
The key to the Minuteman win was actually conducting the initial static test of the second stage motor in concert with the proposal submittal from TRW to the Air Force. This had quite a bit of downside risk in the event that we did. If we had failed, we would have most likely lost the contract. But if we had succeeded, we would most likely win, and we succeeded. Took a lot of effort to do that. Took a lot of support from the corporation, a lot of support from both companies. but I think the results warranted the effort.
Under the leadership of TRW, CSD partnered with Thiokol to remanufacture all 3 stages of the Minuteman III missile, incorporating new and environmentally friendly technologies. The program maintains the only land-based deterrent of the nuclear triad. Another program leading CSD into the future is National Missile Defense, or NMD. NMD provides 50-state defense against limited missile attack by nations or groups hostile to the United States. The program is important in this post-Cold War era, particularly because of the proliferation of missile technology and weapons of mass destruction. In 1998, Boeing selected CSD's Orbis 1 booster for Stage 2 and 3 on the NMD system. CSD's successful strategy included adaptation of off-the-shelf components from its other programs. The Orbis 1 motor, which enjoys 100% mission success, was originally developed as an upper stage for a strategic target missile. But CSD's future isn't built solely on strategic and tactical defense systems. The Orbis 21D solid propulsion system is used as an upper stage for the Lockheed Martin Athena launch vehicle. The 21D is a low-cost commercial derivative of the Orbis 21 upper stage motor. Its burn time of over 2.5 minutes makes it the longest burning solid rocket motor available. With a demand for reduced time to target and greater penetration capability, the nation needs a faster weapon system. CSD's state-of-the-art technology provides across-the-board experience in air-breathing hypersonic, ramjet, and scramjet propulsion to meet those needs. And today, there is a renewed interest in the use of hybrids for launch boosters and divert systems. CSD's 40 years of experience, including over 30,000 test firings, makes it the leading contender for the development of future hybrid systems. Today, CSD's proven hardware is functioning across a wide spectrum of rocket propulsion applications. This great propulsion company has made and will continue to make extremely important contributions to the security of the nation and our allies, and to the advance of science and technology in space. Our valuable past reminds us of our exceptional achievements and strengths, and of all that we have learned. Our capabilities are proven, and we are clearly positioned to continue providing the best propulsion hardware for any customer, for any mission.
As you've just seen, CSD has a proud heritage. With our current mix of programs, we're well positioned for growth in the future. Our objective then is to seize the moment, reach out for the new challenges before us, and continue in this legacy of success.
As our past shows, we will continue to face challenges, but this company's future is secure because of our legacy, its people, their ideas, and because others now and in the future will meet those challenges and overcome them with ingenuity and determination.